Welcome to the presentation on the paper More Than Accuracy Towards Trustworthy Machine Learning Interfaces for Object Recognition. I'm Hendrik Heuer, and this is joint work with Andreas Breiter. We're both from the University of Bremen in Germany. In this paper, we investigate the user experience of visualizations of a machine learning system that recognizes objects and images. Trustworthy machine learning interfaces for object recognition are an important issue. The risks associated with such systems range from a cluttered photo collection to blind people becoming misinformed and self-driving cars hurting people. These risks directly connect to the complexity of deep neural networks, which are employed for many of such tasks. An HCI perspective on how to expose machine learning systems that learn from data to users is only emerging. Our goal with this paper is to examine the user experience of simple visualizations and their influence on trust. This is important since even good systems can fail in unexpected ways, as misclassifications on photo sharing websites showed. Image classification systems in consumer products like Flickr and Google Photos gained sad notoriety for misclassifying people with dark skin as apes and gorillas. In this paper, we explore what visualizations need in order to be perceived as transparent and trustworthy, which visualizations support the users in assessing the performance of object recognition systems, and how different visualizations affect the user's trust. Following Luhmann, trust is an important way to cope with risk, complexity, and a lack of system understanding. This work relates to algorithmic bias, which was found to severely limit the perceived performance of machine learning systems. While there are many great examples for visualizations of neural networks aimed at improving algorithmic awareness by showing the decision boundary, visualizing the filters, or providing explanations, such visualizations are highly specialized and usually presented without an empirical basis for their helpfulness. In our study, we exposed users with a background in machine learning to 3 visualizations of 3 systems with different levels of accuracy. The systems were trained on the CIFAR-10 dataset. Participants were shown 1 image and 1 visualization at a time. Here are the 3 visualizations that were presented to the expert users. The top 1 visualization shows the prediction with the highest probability. This visualization minimizes complexity and cognitive load by giving a simple, action-oriented answer to the classification task. It is similar to the user interface of object recognition systems like Google Photos. Top 3 shows the top 3 predictions ranked by their probability. We hypothesized that top 3 would allow participants to make a more informed decision about the ML system, since participants can use the ranking to compare the predictions. Prop 3 shows the same ranking and visualizes the probability of each prediction using a bar. The probabilities are based on the activation of the softmax unit of the convolutional neural network, which represents the probability distribution over 10 different classes. Prop 3 was selected since it visualizes the probability distribution computed by the machine learning system, thus exposing that such ML systems operate in the regime of probabilities and correlations. For the study, we recruited experts from 2 groups. We had 50 machine learning students, 13 male and 2 female, who were recruited at a large campus university in Germany, and 5 machine learning engineers, all male, which were recruited from a German augmented reality company with a machine learning focus. In interviews, we explored how the visualization helped users assess the accuracy of systems in use, and how the visualization and the accuracy of these systems affected trust and reliance. We coded the qualitative data using an inductive approach, where we read the raw data in detail and clustered textual quotations to identify emergent themes. The first research question was which of the visualizations help users with a background in machine learning assess the performance of machine learning systems. We found that all participants considered Prop 3 to be the most helpful visualization. Top 1 and Top 3 were never mentioned as the most helpful visualizations. Top 1 was considered to be the least helpful visualization by 66% of the participants. The second research question was what makes a visualization helpful for the assessment of machine learning systems. For this, we collected statements related to the criteria and strategies that the participants applied to assess the ML visualizations. These include counting errors or counting correct classifications, which were commonly cited as ways to assess the accuracy of an ML system. Users also took the frequency of errors and their severity into account. A large group viewed it positively when the wrong predictions were at least plausible for them as humans. Animals, for example, should yield other animals. Mistaking a cat for a dog was considered to be less severe and better than mistaking a cat for an airplane. Furthermore, we explored the role of probability. A large group of participants stated that they used the probability of a prediction and its visualization as an indicator to make their decision. We also examined ways of showing how the system works. Displaying probabilities was seen as a big improvement. The Prop3 visualization showed that the system does not have a crystal ball that tells the truth, but that it is, quote, all about probabilities. We also found that a compromise between clarity and the amount of information displayed needs to be found. The third research question was, how do the visualization and the accuracy of a machine learning system affect users' trust and reliance? We found that a large fraction of our participants equaled trust to accuracy. Trust was based on observing a match between the prediction of the system and their classification of the image, a function of accuracy, or somehow connected to accuracy. Trust was described as giving up agency and letting the system make decisions on behalf of the user. Participants also connected trust to feelings and intuition. For the discussion and the key takeaways, we will consider what our results imply for the design of trustworthy machine learning interfaces. We found that trustworthy machine learning interfaces should show an appropriate amount of information, account for unexpected errors, and expose how the system works. Errors of the system could be used to communicate system performance. Semantically implausible errors, like a cat that is misclassified as an airplane, could be used to alert users about situations where a system is not trustworthy. The results showed that participants prefer visualizations that expose the statistical nature of machine learning systems by indicating the probability distribution of the top 3 predictions over action-oriented visualizations that only show the top prediction. Such systems should expose the probabilities computed by the machine learning system. Optimizing the plausibility of errors and designing the error cases could be an alternative to explanations of the decisions of machine learning systems. Plausible errors could increase trust in the system, while implausible errors could lead to distrust. The objective function of a neural network could be adapted to penalize errors that users regard as plausible and reward errors that users perceive as implausible. This could convey the system accuracy through the predictions of the machine learning systems. Thank you very much for your attention. You'll find more information in the paper More Than Accuracy Towards Trustworthy Machine Learning Interfaces for Object Recognition. All the best from Bremen, Germany.